In this video, I'm going to talk about sigmoid or S-shaped curves in relation to enzyme kinetics. So just a reminder again of the notation, I use capital letters E to indicate the name of a species, and I use the lowercase version, like little e, to represent the concentration of the species. I do this to avoid using square brackets. So square brackets is usually used to indicate concentration, but we have so many concentrations to list that the brackets would clutter everything up, and so instead I'm using just a lowercase letter. Okay, so let's revisit the Michaelis Menten equation. So this is the hyperbolic equation. Well, hyperbolic response, this looks like this. Okay, so we have the Vmax, which is the maximal rate. In this case, it goes up to 1, so the Vmax is 1. S is the substrate concentration, and Km is the substrate concentration at half maximal velocity. So if I take half maximal velocity, which is 0.5, take a line here, drop down here, that's basically the Km here. Now, so what I want to do, I want to ask this question. So what is the fold change in substrate concentration S that changes the rate of reaction from 10% to 90% of maximum? Okay, so 10% to 90% of maximum. So 10% of the reaction rate is about here. 90% is about here. So I'm asking, so if I pull a line there and I pull this line here, let's pretend it's here, but it's actually way over there. And I drop down a line. Okay, so these two lines are at 10% and 90% of the reaction rate. These are the substrate levels of those 10% and 90%. So I'm asking is, what's the fold change going from here to here? So this is about 28, and this is maybe about 1. So the fold change would be 28. Okay, so I want to know what that change is, given we move from 10% to 90%. So how do we do that? Well, first of all, I'll just normalize. So I had this one here, which had a Vmax here, but I'm going to divide both sides by Vmax to turn this side into a 1. So the whole thing ranges from 0 to 1. Okay, so I've just divided by Vmax, and now everything will, on both sides, will range from 0 to 1. That makes it easier for me to talk about 10% or 90%. So for the 10% reaction rate, all I need to do is put 0.1 on this side, because remember it goes from 0 to 1, so 0.1 is 10%, and set it equal to that. For the 90%, I just make this 0.9 equal to that. And then all I have to do then is solve for S, and this is actually quite straightforward. I can multiply both sides by Km over plus S, pull the S's onto one side, and I end up with these two. So this is the substrate concentration that'll give me 10% of the reaction rate. This is the substrate concentration that'll give me 90% of the reaction rate. And they're given by 1 over 9 times Km and 9 Km. Now to get the fold change in substrate concentrations, I just need to divide this one by this one. If I divide this by this, the Km's cancel, the 9 comes up to the top, and so 9 times 9 is 81, which I have here. So, okay, to get the fold change, I divide S90 by S10, which gives me that. Km's cancel, and I can work that out as 81. So in other words, what that means is, in other words, to change the reaction rate from 10% to 90% of maximum, which is the Vmax is the maximum, we need to change the substrate concentration 81-fold. Okay, so if, for example, at 10% my substrate concentration were 2, I'd have to change the substrate concentration by 81-fold, which means I'd have to change it to 166. All right, so that's what that means. Okay, now the fact that it's such a big number, right, it takes a lot of a big change in the substrate concentration to go from 10% to 90%, suggests that the Michaelis Menten or hyperbolic response is relatively insensitive. All right, so it takes quite a big change in the substrate concentration to go from 10% to 90%. How can we improve this? Actually, it's quite straightforward, and this is where the main focus of the video is. We use an S-shaped curve. So What I have here, I have the Michaelis Menten, right, which is the hyperbolic curve, and I have here an S-shaped curve, okay? Now I've arranged it so they're comparable, okay? So this has not been fudged in any way. This is the equivalent S-shaped curve that corresponds to this hyperbolic curve. Now, this line here marks the 90% line for the substrate, and this line for the hyperbolic curve anyway, and then I go down here, follow down this line here is the 10% line for the hyperbolic curve. So in order to go from, and then remember this is 10% here, this is 90% here, so in order to go from here to here, I have to multiply the whatever the substrate concentration is here 81 times. All right, now let's look at the equivalent for the sigmoid curve. So the sigmoid curve, the intersection for the sigmoid curve, for example, on the 10% is here. So that's the 10% for the sigmoid curve. And for the 90%, this is the 90% line for the sigmoid curve. Now, as you can see, this distance here is much, much narrower than this distance over here. So it's much easier for when using a sigmoid curve to go from 10% to 90%. In fact, that's I don't know, it's two or three fold change compared to an 81 fold change. Much easier. All right, and that's one of the key characteristics of the S-shaped curve or the sigmoid curve, is that it's much more sensitive to changes in the substrate concentration. Okay. Now I haven't given you the function for this, for the sigmoid curve, and you know what the function is for the hyperbolic curve. It's this one. So I haven't given you a function for the sigmoid curve. It turns out it's not that difficult to do. There are different ways you can use to produce an S-shaped curve. The arctan function is a classic, especially amongst the neural network people, or the logistic equation. Now, in molecular biology, the most commonly used equation for generating an S-shaped curve is the Hill equation. All right, I'm just going to state it here without a derivation for now. But you see, it's not much different from the Michaelis Menten equation. In fact, if you look at it, the only difference is that the substrate concentration has been raised to a power. Change the name of the Km to Kh, and it's raised to a power of n as well. Okay. N basically determines how the sigmoid curve is. So let me just spell out what these constants are. So Vm is the maximum velocity as before. The n is a special number. It's called the Hill coefficient. And then the Kh is similar to the Km actually. Kh is the concentration of S that gives half the maximal rate velocity. Right? So that's pretty much very similar to the Km. All right. So it's the concentration of substrate that gives half the maximum velocity. Remember this one here. So this is half here. So that's half the maximum velocity. That's the Km for a hyperbolic curve. You do the same for a sigmoid curve. I guess I can show it here on this one. So here's one, half is around here. So we take the line across here. That's the Kh. Okay. All right. So here I plotted some curves for different values of n. So it's just a reaction rate versus the substrate concentration S. N equals 1. This is the normal hyperbolic or Michaelis Menten curve. The minute I increase n to 2, though, I'm starting to get a sigmoid curve or an S-shaped curve. In fact, at n equals 8, it becomes quite sharp. In fact, I can keep on increasing n, and it gets sharper and sharper and sharper. Okay. So I can make any kind of S-shaped curve I want just by changing n. Out of interest, the Kh term, this term here, basically moves the curve back and forth. All right, so that just moves it back and forth, but it's the n that changes the S shape. All right. So let's have a look at the fold change then for this Hill equation. So I'm going to do the same thing again. I'm going to set 10% and 90%. I'm going to solve for S. This again is fairly straightforward. It's worth doing the algebra. Basically multiply both sides by the denominator, bring over the s's, and you'll end up with an Sn, and then take the square root to the nth power on both sides, and you end up with that or that one. Okay, and you'll see that it's really similar. Where is it? Very similar to the ones we did for the Michaelis Menten. So if you look here, it's pretty much identical except for the power. Okay, so this is the 10% one. They're the wrong way. They're upside down here. But look, this is the 0.1 here. It's kh divided by 9 to the power of n reciprocal, and here it's 1/9 reciprocal times km. So these are pretty much identical except for the power term. All right. Now to get the fold change, I need to divide this by this. That again is quite straightforward, and you get 81 to the power of 1/n. Right, note that when n is 1, I basically get 81, which is what I had before. Now this, I haven't mentioned this before, but this ratio is sometimes called the cooperativity index. Okay, and is the S-fold change required to go from 10%, not 0.1%, to 90% of maximum. Okay, so let's have a look at some of these fold changes then as a function of n. So down here I've got a table here. I've got the Hill coefficient 1 to 8, and this is the fold change, or the R value. So remember that when we have a hyperbolic response, the fold change was 81. As I increase the Hill coefficient, you notice that the fold change drops and drops and drops and drops. In fact, when the Hill coefficient is 4, I get a fold change of 3. And if we look at the graph, where did I put it? So here it is. This fold change here, remember we said it was something like, I thought it was between 2 and 3. It's actually 3. So if I take this number and divide by this number, I'll get 3. All right. So in order to go from 10% of the rate to 90% of the rate, I need to multiply the substrate concentration by 3. Much smaller than trying to go 81-fold. And you can see it drops and drops and drops. But at Hill coefficient 8, I only need a 1.73 fold change. Okay. Now I haven't shown you where this Hill equation or Hill function came from. It's got an interesting history. Obviously, it was somebody called Hill who first introduced it. Now, if you look at the paper, which is from 1910, Journal of Physiology. Okay, so it's the possible effects of the aggregation of molecules of hemoglobin onto its dissociation curves. You'll find that Hill basically just stated this equation as one possible way to generate S-shaped curves. He didn't say where it came from or how it was derived. So in his own words, he said, my object was rather to see whether an equation of this type, meaning the Hill equation, can satisfy all observations than to base any direct meaning on the Hill coefficient n and k. Okay, so this is empirically derived, or he just pulled it out of his hat and stated it. Okay, so he just stated the Hill equation. Now later on it was suggested, there were suggestions for a mechanistic model, but they're pretty unrealistic. But let me just show you what it was. So consider an oligomer, that is a protein with n subunits and a binding site on each subunit for ligand S. So this is where things get a bit crazy. If you make the rather unrealistic assumption that all n sites are bound simultaneously, then we can represent this situation using the following chemical scheme. So free enzyme plus n ligands gives the enzyme ligand complex. So n could be 1, 4, 8, whatever it is, and that means there will be 8 or n ligands bound into this complex. Now the chance of this happening is pretty negligible. There's no way that 4 ligands could all bind simultaneously. But anyway, let's assume this is possible. If I assume rapid equilibrium, I can write down the association constant. So that's just the association constant for this reaction is ES divided by that times that. But because I have a stoichiometry of n, I have to raise s to the power of n. Okay. I take note of the conservation law. The total amount of enzyme is ET. And so I can compute the fractional saturation. Right, by basically substituting, getting rid of the E and ES terms using this, and I end up with this ratio. So this is the fraction of bound ligand to the total ligand is given by this relationship here, and basically this is the same one as we saw before. So instead of using the association constant, if I use the dissociation constant, which is just the reciprocal, I end up with this. All right. So this is the Hill equation where Kd is the dissociation constant. So just to remind you again where this came from. So the Hill coefficient has this rather unrealistic model where it assumes that all n ligands, let's say 4 ligands, bind simultaneously to the protein binding sites. So if n is 4, there will be 4 binding sites on E, and by some miracle, all 4 ligands bind E simultaneously to produce the full complex. Not very realistic. So often the Hill equation is actually treated as an empirical equation. We don't try to give it meaning, just that the Hill equation does describe pretty well S-shaped curves. All right, so we end up with this. So in the literature, you'll see this form, Vmax, substrate concentration to N, and then the Kd rather than Kh. So Kd is not raised to a power. Okay. Now you may be wondering, what's the relationship between Kd and Kh? That's not difficult. Kh is a better one to express it in because Kh can be sometimes measured. But it's not difficult to find the relationship between the two. All we have to do is set the left-hand side of the Hill equation to 0.5, okay, and then find the relationship between S and Kd. And if you do that, and again, the algebra is not difficult to do, we end up this square root equation. So the square root is to the order n. So this now, because we set the left-hand side of the Hill equation to 0.5, this is the substrate concentration that gives you half maximum velocity. So therefore, I define this to be Kd. I basically say this is Kh. I then raise to the power of n both sides. That gives rid of the square root on here and puts the power on here, and I end up with that. Okay, so the relationship between the Kh and the Kd is this. Remember, the Kh is the substrate concentration at half maximum velocity. So there are different forms you'll see the Hill equation written in. You'll see it in terms of Kh like this. You'll see it in terms of Kh like this, where we've divided top and bottom by Kh, or you'll just see it in terms of Kd. Okay. There are even other variants I've seen, but these are the main three. And as I said, the advantage of Kh over Kd is that Kh has an advantage because the half maximum activity can sometimes be measured directly from experiments. Now, it's difficult not to also mention something called the Scatchard plot. I don't want to mention this too much because it's not something we should be using, but people were interested in estimating these numbers, especially the dissociation constant or the Kh, and they invented this thing called the Scatchard plot. So you have to remember, this was invented quite some time ago, but before the advent of the desktop computer, where you could plug things into Excel or MATLAB and get it to fit the curves, researchers used instead a Scatchard plot. And the advantage of a Scatchard plot is that it gives you transforms the data into a linear line, and it's easy to plot a linear line by hand and get an estimate for the parameters. So let me show you where this came from. So for example, let's say we have a protein that binds a ligand S to give a protein ligand complex. We note that the total amount of protein is the free protein plus the protein complex. Okay. If you assume that the binding is in equilibrium with a dissociation Kd, then the fraction of protein bound to ligand can be shown to be equal to this. So we've seen this derived many times. This is the complex form, and this is the total. So that's the fraction of protein that's in complex form, and when you do the algebra, it turns into this. We've seen this many times. So I can turn this thing here is basically PT, so I can multiply both sides by PT. I can rearrange this, okay, in this form. All right, so it's not too hard to do this. If you look at this and do some rearranging, you'll get this. Now this is a straight line because that's y equals, that's the mx, and that's the b. Okay, so this is a straight line. So if I were to plot ps over s, that's the y, versus the x, which is ps, all right, the negative there means that the slope is negative, so I get something like that. The slope will be minus k, all right, 1 over k, sorry, all right, and the y-intercept, which you can work out to be, which is this here, is also 1 over k. It's 1 over kd. Okay, so you can imagine, right, people measuring the amount of bound ligand, the amount of substrate they're adding. They plot the ratio of bound ligand to ligand versus bound protein, and they'll get a straight line. And so you can you can put a ruler through here. You didn't need a computer to do this, and you could then measure the slope to get the constants. Okay, now if there's any sigmoidicity, in other words n is greater than 1, the result is a non-linear scatter. So if it's an S-shaped curve, you'll actually get something that looks like that. Okay, so it's sort of an inverted parabola. I don't know if it is a parabola, but it's an inverted curve like that. So it can be useful for detecting whether the data shows any sigmoidicity or S-shaped like curve just by looking at the shape of the plot. I wouldn't recommend it for anything else, so I would say the scattershot plot can be useful as a visual aid, but it's not very good at estimating the parameters. The reason are statistical and issues of interpretation. So in fact, I recommend do not use the scattershot plot if possible, even though you'll see it widely described in the literature and on other YouTube channels. Don't use it. There are major statistical issues with it and significant issues regarding interpretation. And often you'll find people misuse it, so I don't use it. The alternative then is just to use more modern non-linear fitting methods, which I won't go into here, but you could even do this on Excel. I think you can do a non-linear fit of the data, and that's a much better way of doing it. Okay, so that's all for now. Thanks very much for listening.